seen these types of numbers recently. Data is exploding all over the world, and for many of us individually. And the storage system vendors have accommodated that growth with very scalable systems, petabytes and petabytes, terabytes and terabytes, even yottabytes. So it's problem solved, right? What's missing? It's really still very hard to afford to store all the data that's being created today. And the goal is, for many people out there, is how to get more out of the storage that you already have. How to find what's valuable, the classical needle in the haystack problem, and how to move and process data through a global workflow. How to securely share data amongst global collaborators, and how to make sure that data is authentic and unaltered. And how to eliminate data that's stored in these big data lakes that isn't valuable anymore. Metadata is the key. Metadata is data about data. It allows you to find the data that you're looking for, and most importantly, it allows others to find the data that you've created. I use this slide to demonstrate the power of metadata. All these CDs could have the exact same data on them, and the CD on the left has no metadata, so you have no idea what's on that CD. Then, as many of us have done with a little bit of a Sharpie, we can describe what basically is on that CD in the middle, some songs that we enjoy. And then finally on the right, there's a commercial CD with a lot more rich metadata, the number of songs, the title of the song, the length of the song, where it was recorded, when it was recorded, etc. And this is a very powerful tool. When you have that much metadata, you can go back and find the things that you're looking for, find the song that you're looking for, or find the data that you're looking for. It turns out, for most storage systems out there, the type of metadata that's available are just basically 4 basic things: the file name, the owner, when it was created, when it was last accessed, etc. What people in these data-intensive workflows need is very rich metadata that describes the data more specifically with higher precision. This is an example from life sciences. This is the type of output that people are looking for in life sciences of a genome sequencer. And with this type of data, when it's tagged to the actual output of the sequencer, they can go back and forth in time and find the exact data they're looking for, and see how to track data through a processing workflow. Just after that. So, in the scientific and technical fields, one of the biggest creator of big data is the oil and gas industry. And they are known, because they've been doing it for decades, and because the data that they're acquiring is such high value, to have a very well-known way of tagging that data with the file name. And they're amongst the most rigorous fields in the world of big data that do that. So you can see here is an example of how that data is stored, metadata is stored in the file name. You can see various things there. But what I wanted to show you is that even though that's so rigid in the way they do it, and so well defined for a file name, that it's very similar to just doing that on a CD. And so most people that store data in these types of file systems, this is the best that they have. And most of them actually worse than that. So for most of these large data lakes that are out there, file systems that are out there, it's very close to having a blank CD. They actually have no idea what's in these huge file systems as they're accumulating over time. So it turns out that big science, Sverre and his colleagues at CERN and others in physics and astronomy, are the high priests of metadata. They've been using these techniques since the mid-90s, right when the internet was deployed. And we've all seen the big famous Large Hadron Collider and all the huge amounts of data that they were able to generate, petabytes of data per second. And on our end, out of General Atomics, where I'm from, we support a fusion research group, and you can see the amount of data that we collect from our fusion reactor. That's about the size of this room here, and you can see all the instruments that we're grabbing and processing that data and moving it through a workflow to hundreds of institutions around the world. So, give you an example of how important metadata is at CERN. They actually developed to support these experiments that we've all become familiar with, the famous discovery of the Higgs boson. They developed 3 metadata systems supporting their 2 storage systems. The conditions and configuration metadata for Atlas, the Atlas metadata interface, and TagDB, which is the actual data that is produced by the systems. And then we've all heard of deep cache and Castor. It turns out that one of the big data boasts of the Large Hadron Collider was this petabyte of data per second. But no one could store, seconds and seconds and seconds of petabytes of data. So what they did is to make sure that the data that they were capturing was valuable to move through the rest of their pipeline, was to create this conditions metadata system that made sure all the detectors and all the other parts of the experiment were working, so when the collision occurred, they knew that that data was good, and they could move that off into the system. And they did that through metadata, and they had this scoreboard and made sure that everything was green and everything, and then they would capture that data and process it and use it for their final research results. Here's an example from astronomy, and if physicists are the high priests of metadata, the astronomers were their first disciples, because when NASA needed to go and start capturing all this data coming down from these large detectors, the first one, the Hubble Space Telescope, instead of developing their own database tools, they went to NASA. They went across the peninsula from NASA Ames over to Stanford, and from the bar experiments at SLAC, they just used those metadata techniques. And so this is the metadata that's used in the Hubble Space Telescope. You can see how rich it is and everything. And the power of this metadata is shown here on this slide. This shows you that since the Hubble was first launched in 1990, coming up to modern times, is that they're actually generating more current research papers on archival data from data that was collected 10, 20, 30 years ago than what's happening now with current general observations. And going back a few slides to the oil and gas field, as we've all heard and seen, is that the techniques to find oil and gas now in already surveyed areas is increasing dramatically. They can go back, and where they've given up in the past, where these oil wells are dry, they can now go in and with all these new techniques and bring the hydrocarbons out much more efficiently now. Problem is, in the oil and gas industry, that previous slide I showed you where they just have the file name as describing the data that's there, they can't do this. They can't go back to the data that they surveyed 10, 20, 30 years ago and find the data that they're looking for, because all they have is that file name. They don't have this type of rich metadata. So now what that industry is doing is trying to figure out, how do I go back and get all these tapes and archival information where I just have the file name and decorate it with this type of metadata, because I want to be able to go back and go to all the areas I surveyed in the past and find the right conditions to find oil again. And they can't do it. And that's the power of these types of techniques. And then last year around this time, maybe many of you have heard this, there was this famous Kepler spacecraft that was looking out in space and locking onto large star fields and looking for planets going around various stars out there in space. When the planet went in front of it, it would cause a little drop in intensity, and then that way they could find Earth-like planets in the Goldilocks zone with suns and planets like us. And about a year ago, the satellite stabilizers failed. And I remember listening to a radio show right around that time where the interviewer was like very sympathetic to the principal investigator from NASA Ames, like, "Oh, we're so sorry to hear the spacecrafts have failed." And what was striking to me was the investigator was like, "Oh, no, we collected so much data, we're so happy." Just the difference in perspectives on the two things. It turned out that they did collect so much data and have so much metadata they tagged it with. I don't know if you remember this, but earlier part of this year, they came out with their big announcement that they found hundreds of Earth-like planets in the universe, and they're continuing this type of analysis because of all the metadata that they captured. So These big science efforts are global organizations, and they have lots of people to develop these special purpose tools. How can those techniques now be used for more common things that are going on out there? There's two types of general purpose frameworks or systems that support user-defined metadata and copy the techniques used in big science. One is an open source toolkit from the University of North Carolina called IRODS. Another one is a commercial product from General Atomics called Nirvana. And they both come from a project called SRB, Storage Resource Broker, based out of the San Diego Supercomputer Center. And the reason why we're involved is because we used to run the San Diego Supercomputing Center, and the people that developed this were employees of our company, and we use it to support the physics research that I talked about before. This is how these systems are configured architecturally. They may have different names, but basically there's a storage resource here that could be a NFS file server, a ZFS file server, Lustre, UPFS, ZFS. And there's an agent that sits on that device and then maps the data, the files that are on that data, to the metadata stored here in the metadata catalog. And then there's also a relational database like Postgres or Oracle to support the tagging of the row of data to the file that it's supporting. So all the metadata that we talked about, these 20 or 30 different pieces of metadata, are individual columns of a data row in a relational database. Then there's some kind of interface with either the program or the user to go in and do SQL type of queries into that database to find the data that people are looking for. So when you have this type of system, you can support these type of global workflows. All these types of domains are all very similar. They have a big data generating sensor, and then that data is ingested, and then it goes along into a workflow that includes processing. This is like a Lustre file system into a cluster. Then the results of that processing are analyzed and shared in a shared file system, and then it's eventually archived to slower, higher capacity storage all the way up to tape. And so these types of metadata systems can move data in these workflows, and can also track the data, who's accessing it, provide certain access levels, and detect when data has been modified through the workflow. I'll just skip that. So one of the things that's very important in a lot of these fields is provenance, being able to track data through the processes and the transformations, especially in life sciences now, as in genomics, as it's moving from research into clinical use where therapies are actually being developed. The pharmaceutical companies have to comply with certain regulatory requirements that tracks the data that was used in the development of these therapies to make sure that the data was never altered in the results of the therapy. This is the most successful use case for these types of products. It's pretty universal now. This is a classic phenomenon that's happening across all these different areas, is that over time, because the storage industry has made it so easy for people to store so much data, human nature as it is, people are storing it. And so what happens over time is that you get tens of millions of files from hundreds of past users and current users and past projects and current projects. So people basically, at the end of the day, don't know what's happening, what's really in all this data that they're storing. And they're afraid to touch it because it could be important, and so they just buy more storage. And we're actually do that ourselves at General Atomics. So the use case in this case is these types of technologies can be used to scan the file systems using the existing basic storage metadata I just talked about, and generate reports on what data is in there, when it was last accessed, who created it, what project, etc. And we ourselves use this. We have a very expensive enterprise storage system to capture the data coming out of our experiments. We were running out of storage, and we were about to go and buy some more expensive storage to support it. And we used our tool, Nirvana, to analyze the data that was in the file system. Found out that 65% of the data hasn't been accessed for years. One investigator created half the data in the system, and we were able to let the manager of the system see that, and what he was able to do was take the data that wasn't accessed for years, put it onto tape, and then instead of buying another enterprise storage system, these schema on read. But this, I think, in general, is going to be much more common that people are going to be aware of moving forward, just because of the sheer size of all the data generated in these types of workflows. And the fact is that with the limited amount of file system metadata that's available to people, they won't be able to find it and manipulate it in the ways they want it to. And so I think you'll see more and more application-specific metadata in these types of workflows, and it'll become more common and not just for the big scientists anymore. Okay, thank you very much.